Hello and welcome to yet another video where we are going to look at a topic which I consider to be important because it is one of those topics that gives students a lot of challenges, and this is the photoelectric effect. I won't teach you the whole topic. I will just go through the areas where I feel students normally make a mistake, they find a challenge and that kind of stuff. What is photoelectric effect? Photoelectric effect is the removal of electrons from a metal surface when electromagnetic radiation of a suitable frequency falls on the metal. Removal of electrons from a metal surface when radiation of suitable frequency falls on the metal. Because there are two methods by which electrons are removed from a metal surface. One is thermionic emission, the other one is photoelectric effect. So this topic here, or this part here, is on photoelectric effect. It's a topic in Form 4, Chapter 39 in our syllabus. Now, without wasting time, let's go straight to questions because I want to address these using questions. The first question here is you're given an electron in an excited atom, falls from energy level E1 to energy level E2. Now, around an atom, there are various energy levels that an electron can occupy. And when that atom gains energy from an external source, maybe it's being heated, maybe frequency or radiation of a particular frequency falls on it, the electrons gain energy and they move further away from the nucleus. The more energy they gain, the further away they move from the nucleus until at a particular point they are completely removed from the atom. Let me just illustrate that here. Now we can consider this to be the nucleus of the hydrogen atom. It's got only one proton and it's got the first energy level where an electron can occupy. This is the farthest the electron can go. The electron is somewhere around here. There exists energy levels, although they are not occupied, they are there around that particular atom. Different energy levels, and as you go away from the nucleus, these energy levels are closer and closer and closer and closer. This atom gains energy or absorbs energy. It is absorbed by this electron, so the electron is promoted to a higher energy level. Maybe let's say there is an energy level here. Now, when this electron falls from that energy level to a lower energy level, it emits electromagnetic wave. This is the initial energy level, which we can call E1. This is the final energy level, E2. Remember, when the electron gains energy, it moves away from the nucleus, but when it falls towards the nucleus, it releases that energy that it had gained. The energy released is equal to the difference between the two energy levels, and in order to get that difference between the two energy levels, which is delta E, we do the final energy level minus the initial energy level, and this energy which is released is equal to Planck's constant times the frequency. And in this particular question, we were just asked to, we have an electron in an excited atom, falls from energy level E1, so E1 is the initial energy level, to energy level E2. Write an equation relating the energy change to the frequency f of the radiation emitted. Explain the symbols used. So the change in energy is equal to Planck's constant times frequency. This is equal to the final energy level minus the initial energy level, which is E2 minus E1, and Planck's constant is h, and frequency is f. It's just as simple as that. That was not difficult. Let's look at question number 2. In an experiment on photoelectricity using metal X, the graph shown in figure 9 was obtained. Use the graph to answer the questions 1 and 2. When we are still on this question, one of the questions we asked is to determine the minimum frequency below which no photoelectric emission occurs. This minimum frequency below which no photoelectric emission occurs is referred to as a threshold frequency. And here we have the graph. We've got stopping potential Vs in volts versus the frequency of the incident radiation. Now, what kind of circuit is used to perform this experiment? We are going to look at that one in question 2. So we get different values of stopping potential versus the frequency of the incident radiation, and we get a straight line like that. You get this line, you extrapolate it backwards like that until it cuts the frequency axis, until it cuts the x-axis. This is the threshold frequency. And when we look at it, we can see since this one is 5, and this one is 10, this is 15, this is 20, then this frequency here must be 2 small divisions is equivalent to 1, 2, 3, 4, and 5. So I can see that here, since this one is 4 and this one is 3, then it is 3.5 by 10 raised to power 14. That will be the value of the threshold frequency, 3.5 by 10 raised to power 14. Let me see whether that is the answer that I got. Yeah, I think there was a problem here. Let's just change that, because I was working at 2 questions simultaneously. I think that is where the problem arose. So the threshold frequency is 3.5 by 10 raised to power 14. The second question was to sketch on the same axis and graph for a metal Y whose work function is higher than metal X. Let's look at factors which affect the work function of a metal. We have just seen that the work function of a given metal is equal to Planck's constant times the frequency. So the higher the frequency, the higher the threshold frequency, the larger the work function. So in order to get this sketch for metal Y whose work function is higher than for metal X, you just need to know that its threshold frequency must be higher than this value. So you know that it must be on this side here. And then the graph must have the same gradient as this one here. So you're going to draw a line which is parallel to this, but on this side. This line must be parallel to this. That is the first condition. And then it must be on this other side, so that should we want to know the work function of that metal, we need the threshold frequency, then we will definitely see that it has a lower value than that one of metal X. That question was just as simple as that. Let's look at another question that was set in a different paper altogether. We are asked to describe with the aid of a diagram an experimental setup for observing photoelectric effect. Here we just want to observe photoelectric effect. Of course, you will need a photocell. This one is a photocell. You will need a galvanometer or a sensitive microammeter. You will need a battery, maybe a 12-volt battery, or an extra high tension. You will need connecting wires. You will need a source of white light. white light has got 7 colors, but then you might need just one of the colors. That is why you will need a filter. So here in this diagram, you'll have to label this part as filter. This is white light, and then after the filter we've got light of one frequency. We call it monochromatic. Light of one color, we call it monochromatic. And the diagram is just as simple as that. So first of all, we are going to cover the photocell. You can even cover it with your hand like that so that it is in darkness, and then observe the galvanometer, and then remove your hand again. You observe the galvanometer, you will see a deflection. You will see a deflection. Now, you must ensure that the positive side of your extra high tension, or this battery here, is connected to the anode. Is connected to the anode, so that when electrons are removed from here, they will be repelled by the negative potential on the cathode and attracted by the positive potential on the anode. So they will be accelerated towards the anode. You must ensure that. Of course, there is something else that we forgot in this particular circuit. We are supposed to have a rheostat. Let's just insert that rheostat there, because as it is, it will not be complete. Let me see whether I can be able to quickly add a rheostat. A rheostat is just a resistor whose resistance can be varied, okay, and therefore it should have an arrow which crosses like this. That is a rheostat. Just that simple. Want a very simple diagram. There I've got the rheostat. Now if we were to connect that circuit without a rheostat, then you realize that you will be short-circuiting the terminals of the battery. The voltage across the photocell will be so big and it can destroy the photocell. So the rheostat is important. So remember, there are pieces of apparatus which cannot be represented with a symbol, such as this, which is a filter, this, which is white light, this, which is monochromatic, must be labeled. You label the diagram. But the other pieces of apparatus, you don't need to label them, because the symbols, it is understood that you know what the symbols mean. So, and then in the description, connect the circuit shown in the diagram. No, that is one of the statements that you can put down. The apparatus listed above are connected as shown in the diagram, ensuring that the positive terminal of the battery is connected to the anode, while the negative terminal is connected to the cathode. When the photocell is covered with a piece of cloth, or when the photocell is in darkness, there is no deflection on the galvanometer. When the piece of cloth is removed so that the photocell is exposed to light, the galvanometer deflects. That is all that you need to state. You know, when the galvanometer deflects, it shows that there is an electric current passing through, and that electric current must be caused by this light which is falling on the photocell. That's all, because we are supposed to observe photoelectric effect. Next, the table shows the relationship between the stopping potential Vs and the corresponding frequency F of the emitted electrons. Okay, stopping potential versus the corresponding frequency. What kind of circuit do we use here? This is the circuit that we would use to do that experiment. This is the circuit. This voltmeter is used to measure the stopping potential. What is stopping potential? It is that potential that just prevents the electrons from leaving the cathode. Now, how do we ensure that it stops the electrons from leaving the cathode? It is because of the way this potential is connected. This time, the negative side of the battery is connected to the anode. Observe that. While the positive side of the battery, if you follow it, you can see that it's connected to the cathode. That is important because we want the electrons which are produced here to be held back by that positive potential. We've connected the positive potential to the cathode so that any electrons removed from the metal surface, they are held back. It's like a magnet which holds them back. It's only the electrons with sufficient energy to overcome that attraction back to the cathode by the negative potential that are going to leave. So if you notice that there is a deflection in this microammeter, microammeter is a very sensitive ammeter, measures very small changes in current in terms of microamps. When you notice that there is a reading here, it means that electrons are still leaving the cathode. So what you're going to do, you're going to increase the magnitude of that stopping potential by moving the jockey this way. By the way, this one is a potentiometer. Like you can see, it's got 3 terminals. 1, 2, 3. All terminals of the potentiometer are connected. And I hope you can remember in the practical session when we were discussing the potentiometer, you know what it is. All the 3 terminals of the potentiometer are connected. And it is the middle one which moves now to and fro. If it moves this way, it's going to increase the magnitude of the stopping potential. When it's moved this way, it's going to decrease the magnitude of the stopping potential. This is the circuit that is used to measure the stopping potential for a given monochromatic light. We have 7 colors starting from red all the way to violet. Therefore, we are going to have at least 5 filters for red, maybe orange, green, blue, indigo, violet, you know, something like that. All those filters there. What do we mean by a filter? We know that white light has 7 colors. When we put a green filter, it's going to allow only green to pass through while the other 6 colors are blocked. Remember, the color of the filter you put there is the one which determines the radiation which is allowed to pass through. So we are going to have several filters. Now, this is how a filter works. A filter is just a card. Let us say it is a red filter. Red filter. In the electromagnetic spectrum, the complete electromagnetic spectrum, we've got colors starting from red, orange, yellow, green, blue, indigo, and violet. 7 colors. When those 7 colors reach the red filter, it's only the red which will be allowed to pass through. Just red. The other colors are blocked. This electromagnetic radiation of one color, the electromagnetic radiation of one color, is what we refer to as monochromatic radiation or monochromatic wave. So, having understood that, we are going to get the stopping potential for red. So we're going to vary the rheostat. So we are going to vary the rheostat until we get a stopping potential, until we get 0 reading on the ammeter, and then we get the value of the voltage across the photocell. That will be the stopping potential. And then we are going to alter the filter, maybe use orange. So this time the other colors will pass through, will be blocked other than orange. We repeat the process and get the values of stopping potential versus the frequency of the different radiations, different colors. So we are going to plot a graph of stopping potential. Vs again is the frequency f of the incident radiation. And then from there we are going to be asked to determine the work function. I think I've already gone through how to determine the work function. Let's see how the graph looks like. So this is how that graph looks like. So there we have the graph of stopping potential versus the frequency. And you can see that this is again a point where we review the ideas of the best fit line. you can see my best fit line passes through this point, very close to this point and very close to this point. It has just missed this point by a short distance, missed this one by a short distance, and the two distances are on opposite direction. However, it passes through this one exactly. It misses this one by this much distance and this one by an equivalent amount of distance. So if a line passes through majority of the points then and misses just a few, those few points must be on opposite side of the line, one above, some above, and an equal number below. Sometimes the best fit line may not pass through any point at all. That means it's going to leave equal number of points below and above. And that is how it looks like. So I'd like you to get that data. Try to get any graph paper out there. Try to repeat drawing this graph. Practice on drawing the best fit line. And you'll be able to see that through that, you'll be able to practice very well, because you find that a graph paper is just given and you're asked to plot that particular graph. And then after that, you are asked to calculate the work function of that particular method that is being used. Of course, we must get the threshold frequency, which in this case appears to be like 1.1 here, 1.1 by 10 raised to power 15 Hz. So, and when it comes to calculate the work function, it will be equal to Planck's constant times the threshold frequency. I should have put a note here showing that that is the threshold frequency, and that work function is 7.293 by 10 raised to power minus 19 joules. You can verify that one by yourself later on. Let me look at the equation which is being used here so that we can be able to understand why we are plotting these type of graphs. Now, this is how the energy of the incident photon, which is HF, is used. It goes to provide the work function, and then it gives that emitted electron some certain amount of maximum kinetic energy. We have already seen that the work function will be equal to H times the threshold frequency, meaning that in this case, for photoelectric effect to take place, the frequency of the incident radiation, which is F, it may be red, green, and so forth, must be greater than F naught for photoelectric effect to take place, because this is absorbed by the metal, and that particular metal must be such that the work function is less than the energy of the incident photon, so that it can use the difference to give itself the kinetic energy of that electron. Now, let's substitute this one here. HF is going to be equal to HF naught, which is a constant, plus, now the kinetic energy of that emitted electron is equals to the charge of the electron times the value of the threshold times the value of the stopping potential times the value of the stopping potential. Now, this quantity here, Vs, is plotted on the y-axis, while F is plotted on the x-axis. So let's separate the variables. So I'm going to start with, first of all, let me write it using starting with EVS. Let me start with EVS plus HF naught is equal to HF. I'm going to make EVS to be the subject of this expression, so I'm going to have HF minus HF naught. And then because it is Vs which is on the y-axis, I'm going to divide throughout by E to get Vs is going to be equal to H over E times F. I've separated these two like this because F all by itself is the one on the x-axis, of course, minus the work function, HF0. This one is a constant. Now, because this one is on the y-axis, let me see whether I can. This one is on the y-axis. This one is on the x-axis. Y is equal to, I'm going to have, the other one will be m plus c. And you can see the value of the gradient. If I go back to that graph and get the gradient, I'll be able to say the value of the gradient of that graph, which is m. M is the gradient, and it is equals to h over e. Since I know the electronic charge, or the charge on the electron, which is 1.6 by 10 raised to power minus 19 coulombs, I'm able to verify the value of this Planck's constant. Now this constant here, we find that from my graph you cannot be able to determine it directly. From this graph, let's see whether you can be able to determine it. You can see that there is no normal scale on this other side, but if we could be able to determine that and plot it like that until we get this particular point by moving the x-axis upwards, we can be able to read it. But as it is, we cannot be able to determine the y-intercept. In such a case, even in the actual practical where you have chosen a scale which does not allow you to determine the y-intercept, you can use this other one here, because this value is the value of f when Vs is 0. The value of f when Vs is 0. Remember that, this one here. Well, this one will be the value of y when x is 0. You can also use this one to get this. So that is all that we had the time for in this particular topic. Look at other questions involving photoelectric effect, and let me know in the comments below whether there's something that you've not understood or something that you want me to emphasize. Alternatively, you can even ask me to cover another topic like most of you are doing. They are constantly requesting that I cover certain topics. So in the next video lecture, I'm going to cover another topic, probably radioactivity or electronics. Bye bye.